Hello, my name is Harris Anatopoulos. I have been developing a hypothesis that tells us how the universe works, from the very small to large cosmological structure. In order to understand our universe, we need first to be able to describe a physical structure and a mechanism at a fundamental level, and that the mathematics we use represents that mechanism. We will see that our universe is a field constructed from just two objects, and that it is a finite open field existing in pre-existing space. We will see how a particle like the electron is formed from the two objects that make the field, and we will see how the fundamental forces all emanate from this field and how they are a consequence of the geometry of the field. My hypothesis talks about how the fundamental structure to the universe has mass. However, its mass does not produce gravity, and we need to understand why this is so. Later in this video, I will be going into exactly what gravity is. Now, the universe is a physical field that has formed from just two objects. The first is lines that have mass. So these lines would be millions of light years in length. However, the width or the diameter of each line is much smaller than the diameter of an electron. Now, they are solid, but they are flexible. The next object that makes up the universe is a particle I call the quanta particle. This also has mass. It's very much smaller than an electron. Its diameter is the same as the diameter of a field line. It's spherical in shape, and it's the most numerous object in the universe. Now, quanta particles are in constant motion because they are elastic objects and are subject to elastic conditions. So their total kinetic energy is conserved. The quanta particle is the energy of the universe. It is the vacuum energy and it is dark energy. Now, the lines in the quanta particle form a field and create a mechanism. But before I discuss the field, I want to demonstrate some fundamental principles of this mechanism. Let's imagine we have two field lines and a number of quanta particles bouncing between them. When a quanta particle hits a line, it bounces off the line, and that also causes the line to move in the opposite direction. So a quanta particle bouncing between the lines causes the lines to move away from each other. So this acts as a repulsive force. However, this force is inverse to distance. The closer the lines are to each other, the greater the force. The wider they are, the weaker the force is. So the tendency here is for the field lines to expand. However, if we add more field lines, the repulsive force is counteracted. The force at column A will push these two lines apart, but the force at column B and C will push them back, creating a counterforce, preventing column A from moving. So there are two principles here. The first is that this mechanism provides an inverse to distance force, and the second one is that it provides a counterforce to the force of repulsion. So we have a conservation of energy. Quanta particles bouncing between field lines are in a similar state to an ideal gas. Quanta particles are all the same size with the same mass. They are constantly moving and moving in random directions. Their speeds vary, but average out to a constant pressure. The average distance between them is much larger than the quantum particle itself. No other forces apply, electric, magnetic, or gravitational. Only a kinetic force. All collisions are perfectly elastic, no conversion of kinetic energy into any other form. At this fundamental level, there is no heat energy, so collisions do not lead to an increase of heat, and pressure is inverse to volume. The combination of the quantum particles and the lines form a field. The lines are orientated in 3 spatial dimensions. The lines are not in contact with each other. What keeps them separated is the quantum particles. Parallel lines are separated by a line orientated in a different direction. So 2 lines next to each other are at 90 degrees to each other. So the field becomes a 3-dimensional structure. The fact that the lines are not in contact with each other means that the quantum particles can move around the field freely. The effect of this is to allow the energy in the field to be homogeneous. Particles like electrons are formed when the field lines are pushed together with enough energy. So when a localized area of the field is compressed, the quantum particles and the field lines in that area are pushed together towards a central point. This compression forces the quantum particles in that area into a central mass, and the field lines are pushed onto and around that mass. So now the field lines encapsulate the mass of quantum particles, and now we have an object that has a much bigger diameter than a single quantum particle. So the field lines in this distorted localized area are no longer at 90 degrees to each other. They are pointed inwards towards the central mass. So the geometry of the field in this localized area has changed, and it's this geometry that allows for a negative energy or a reduction in energy, and this also creates a negative field. Now, when the field is compressed like this, the increase in energy it creates wants to push the field lines back to an undistorted state. If that happens, then the field lines will come off the mass of quantum particles, and that would return the quantum particles back to the field. So what keeps the field lines attached to the mass of quantum particles? Well, as the field and the quantum particles in that area are pushed inward, quantum particles from outside this area come flooding in, and it's their kinetic energy impacting with the mass of quantum particles that prevents the lines from coming off. However, this energy is not enough. It has to be increased, and this is done by the radius. So what the radius does is to create a second distortion by projecting into the first distortion. This in fact creates a positive force. It pushes the already distorted field lines back and closer to each other. This brings us back to the fundamental principle. The closer the lines are to each other, the more energy is created. So now there is enough energy pushing the lines onto the mass and stopping them from renormalizing the field. Even though the force around the radius is positive, the particle remains negative. The positive force is much smaller and the negative force overwhelms it. So a particle is made from a concentrated mass of quantum particles encapsulated by the field lines. So how can it move through the field without the field lines entangling? Well, as we see with figure A, the mass of quantum particles is subjacent to the field. So the mass moves between the field lines. Now, the field is stationary. So as an object moves through the field lines that are holding the whole thing together disengage and are left behind, but they are replaced by oncoming field lines. So even though a particle moves between parallel field lines, it will create drag because there are lines diagonal and across its path. So as it moves faster and faster, it will push the lines ahead of it closer together. This creates more energy between these lines and creates a resistance. This energy that is created ahead of it is the reason why an object's mass increases by mass times velocity squared. But it's not its mass that increases, it's the energy in the field, and as that object's velocity decreases, that energy dissipates. So what we see is an equivalence of mass and energy, and that inertia is the resistance an object creates moving in the field. Now, to overcome the resistance, we need to understand that particles are not rigid. A particle is made from a number of quantum particles held together by the field lines. So particles are malleable. When a particle begins to move through the field, it encounters force in the direction it's moving in. And it's this force that changes its shape. The front of the object contracts in length, and the rest of it elongates. Now, it's this elongated length that pushes into the field much more than the particle's velocity is pushing into the field. This means that the force behind the object is greater than the force in front of it, so it's able to overcome resistance. So the process that forms particles is one in which the energy between the field lines and the lines are compressed towards a central point. And I discussed earlier how the radius projects as a second distortion, creating enough energy to hold a particle together. Now, in fundamental principles, I discussed how there is a counterforce that equalizes the energy in the field, and how the radius, creating that second distortion, creates a counterforce in the distorted field. So the energy in the distorted field, just like the energy in the undistorted field, is equalized. Now, as the field extends away from the center, the field lines are less and less distorted, so the force acting on these lines becomes weaker, so it becomes inverse to distance. This is why you could have action at a distance. Now, when the lines are compressed, only negative particles are formed. Therefore, a positive particle is a composite particle. Now, in order for me to describe how positive particles are formed, a lot more has to be said about individual particles and how they come together to form positive particles. And I will do that in my next video. For now, we will move along with just a basic description. Essentially, a negative particle pulls the field lines in, and a positive particle will push them out. But the force on a positive particle will be balanced from all sides, just like a negative particle, and it would also have a field that extends away from it. So when a positive and negative particle come within the influence of each other's fields, they affect each other's balance of force. The geometry of the negative and positive fields accommodate each other. So the positive field fits into the negative field, but it's not an exact fit. So this weakens the energy between the two particles. However, the force on the other side stays the same. So you have an unbalanced force that pushes the particles together. So there is a reduction in the energy between the two particles that creates a push force on their opposite sides. Now, two positive particles will repel each other because as they approach, they are pushing the field lines between them closer together, and this increases the energy between them and pushes them away. Photons are particles that are created when the field is compressed, so they are just a quanta particle encapsulated by the field lines. So they have mass, they have a field, they are negative particles, and their mass and size is very much smaller than an electron. Now, I showed before how an object moving through the field can maintain its momentum by generating enough energy behind it to overcome its drag. However, there is a different dynamic for the photon. As a photon pushes into the field, it pushes the field lines closer together. This creates a lot of energy ahead of it. It's this energy that then propels the photon at the speed of light. Now, the photon will push into the field at an angle, and the field lines will propel it forward at this angle. So the photon moves in a wave motion and causes a wave motion in the field. So every time the photon is propelled by the field lines, it receives the same amount but a new amount of energy. So the photon gets its speed from the field because it just has the right amount of mass to create enough energy in the field to be propelled at the speed of light. Now, the wavelength of the photon depends on the angle it hits the field lines. A shallow angle will produce a longer wavelength, and an acute angle will produce a shorter wavelength. But regardless of the wavelength, this speed of light is constant. However, the shorter the wavelength, the longer the transverse distance is. So photons with different wavelengths will arrive at different times. Now, every time the photon pushes the field lines together and creates the energy that propels it along, it also creates an opposite and equal amount of energy that continues in that direction. So this energy is not in the form of a photon, but it has the momentum of a photon. It's really just energy moving through the field lines. So it could be regarded as a wave or a long-lasting virtual photon. But its motion will collapse if there is anything in its path. So when you have two slits and you shoot a particle through just one of them, what passes through the other slit is the wave the particle has created in the field, and therefore you get an interference pattern. By observing this, you collapse the wave through the field, and then it's just a particle. So a photon's energy, and therefore its velocity, comes from a slingshot effect from the field lines. However, as I explained before, an object moving through the field will push the field lines ahead of it closer together. This creates a resistance that stops it from getting to the speed of light. So how does a photon travel at the speed of light? Well, the size of a photon is very much smaller than an electron, and the distance between the lines is very much bigger than the size of a photon. So even though there are lines attached to the photon, it has to travel a long distance before it encounters any other field lines. Only then does it start to feel resistance. So while it's travelling between the field lines, the field cannot detect it. During this time, the photon is massless. When it comes in contact with the field responds to its mass. Okay, let's look at an object at rest with no field lines, just quanta particles. So the amount of quanta particles hitting it from all directions is equal. Now, as it begins to accelerate, it encounters more quanta particles from the direction it's moving in. So there is more force from that direction. Now, on the opposite side, the object is moving away from the quanta particles, and therefore there is a reduction in the energy behind the object. So the force of acceleration is a very real physical force. There is more force from the front than the back, and it's this force that begins to change the shape of the object. It contracts the front of the object and elongates its shape. Now with this diagram, the dots represents the quanta particles, and we see that when the object elongates, the amount of quanta particles hitting it is reduced. We also see that the front becomes angular, and this reduces the impact force from the quanta particles. So regardless of its velocity, the value of energy in relation to its size stays the same. Now the back of the object is not angled, so even though there is a reduction in energy on the back, the quanta particles hitting the back are not deflected. So the result of all of this, and as long as there is a constant velocity, the force from the front is equal to the force from the back. What this allows is for the laws of physics to be the same at any constant velocity. Now, for an object to move in the field, its own field must generate a push force from the back to overcome the resistance from the front. However, this means that the two opposing forces are not equal. So, for the laws of physics to be the same at constant velocities, another mechanism must be employed. Now, all objects exist in negative fields. This means that as an object is moving, it's moving forward into reduced energy. So, at a constant velocity, the object's shape does not change. Now, all movement through the field is in a wave-like motion, and this is because of the geometry of the field. However, I'm not going to go into the exact geometry of the field in this video, but I will in my next video, the connection model. Now, first we need to understand linear and transverse distance. Linear distance is a distance measured between x and y in the reference frame of an observer at rest at y. So someone moving between x and y would be in a different frame, and they would be moving in a transverse motion. Therefore, the distance they will travel will be greater than x to y. Now, the faster you're moving, the shorter your wavelength is, and the greater your transverse distance is, and therefore, the longer in time it takes for you to get to your destination. However, moving in a wave-like motion is not the cause of time dilation. Time dilation happens because as an object moves faster, it contracts in size, and this results in more energy around the object. So let's say you're traveling from x to y. It should take you in time, distance over velocity. Now I'm waiting for you at y, and I have the ability to stop you when my clock tells me time is up. What we would find is that because of your transverse motion, you have not travelled as far as we think you should have. Now, I can find in my reference frame, which is the linear distance, how much distance you have travelled by using the Lorentz factor. And my time will be the time we agreed upon before you left. But your time will be dilated. It would be the Lorentz factor times the agreed upon time. In order for me to know when you will arrive, I need to divide time over the Lorentz factor. So I will be waiting for you longer to arrive. However, your time will be the time that we agreed upon before you left. In order for this to happen, more distance must be added between x and y, and this is done by your transverse motion. So linear distance over the Lorentz factor times time times the Lorentz factor will equal time equals distance over velocity. So in summary, the faster you are moving, the more time is dilated and the greater your transverse motion is. Therefore, the less linear distance you will travel and the longer in time it will take for you to arrive. So there is a correlation between velocity, time and distance, and viewed from an outside reference frame, not only does time dilate, but distance and velocity does as well. The speed of light is constant at all times, even when it's moving through a medium. Now, all objects contract the field, so when light moves through a medium like water or even a gravitational field, it has to travel a longer distance to get through it. Now, the faster an object is moving, the more contracted the field around it is, and the longer it takes light to travel through it. But due to time dilation, an observer in that reference frame will measure light moving at the speed of light, because the apparent slowing of the speed of light due to the extra distance it must travel will correlate with the dilated time. However, different observers in different reference frames, if it was possible to see light in each other's reference frames, would measure each other's light speed to be different than their own. Of course, as light emerges from one reference frame and into a different reference frame, it correlates with that contracted field and that field's dilated time. Gravity is a local inward distortion of the field lines, just like the inward distortion around a negative particle. Therefore, it's a negative field. So the field lines are pulled towards a central point. Now, as you move away from that central point, the lines become less distorted, so the force weakens over distance. Therefore, an object entering a gravity field will be affected by the field instantaneously, which allows action at a distance. So, an object falling in a gravity field will in part conform to the field and will also distort the field. The object pushes the field lines above it closer together. This creates more energy above the object, and that energy pushes the object down. Now, below the object, the field lines are stretched towards the central mass. So the bottom part of the object is also stretched as it conforms to the shape of the field. Now, a gravity field is a balanced field, so any object entering it will unbalance it. An object entering on one side will weaken gravity on that side, because the positive force above the object acts against the negative force of gravity. So when one side is weakened, there is more force on the other side. So if you're falling in Earth's gravity, you are accelerating towards the center, but at the same time, Earth is falling and accelerating in its own gravity towards you. First, let's review the force from acceleration. When an object is accelerated, it is impacted by more quanta particles from the direction it's moving in. However, when you are falling in a gravity field, you do not feel that force from acceleration. This means that there is no increasing amount of quanta particles impacting you in the direction you are accelerating in. The reason for this is that a gravity field is a negative field. It has a reduction in energy. Now, if you recall how an object moving at a constant speed moves forward in its own negative field, then gravity has the same dynamic, except gravity is the negative field ahead of the object. Now, as the object accelerates, the energy above it that's pushing it down increases. At the same time, the energy below it reduces, and that's because of the steepening angle of the field lines. So even though the object is accelerating and changing shape, the energy above it and below it maintain a constant ratio. And it's this that gives us an equivalence with a state in which an object is moving at a constant speed where there is no gravity field. In both cases, the conservation of energy is maintained. So an object in orbit has a number of more complicated forces applied to it, and that's because the gravitational field changes the shape of the object. Now, the object is not falling, so the forces around the object are constant. However, they have different values from different directions, and unlike moving at a constant velocity away from the gravity field, there is no negative field in front of the object. So, first of all, as we see in this figure, the object is elongated due to its velocity, and that gives it its push force from direction A. Now, because gravity has force that is inverse to distance, the force at C is greater than at B, and it's this slight difference in force that causes the object to constantly change direction. Now, the force of gravity coming from above the object from direction E is countered by the force hitting the object from the front. So, gravity changes the shape of objects, but objects change the shape of gravity. Now, because of the object's elongated shape, the field lines underneath it are stretched closer together. This increases the force from direction D. So unlike falling in gravity, the forces around an object in orbit are unchanging. So understanding a physical structure at a fundamental level helps us to understand how our universe works, and understanding the geometry of that structure helps us to understand how our fundamental forces are generated. So in my next video, the connection hypothesis, we will see how the mass and the size of particles, along with the fundamental forces, are all connected.